Okay, let's unpack this. We're diving into something pretty wild today.
Definitely.
Imagine looking up, and the sky isn't just, sky. Imagine it's a power plant, a grid, a giant battery, even managing the climate.
It sounds like pure sci-fi, doesn't it?
Totally. But it's a concept called the Atmospheric Energy Lattice, or AEL, developed by Mr. Shahryar Ghiasi. And the sources we've looked at explore how this could, well, fundamentally change everything about our atmosphere and energy.
And what's really fascinating, I think, is how it tries to hit multiple massive challenges at once. Not just power generation, but storage, distribution, even climate concerns, all integrated.
Right. So our mission today for you is to cut through the sheer complexity here.
Yeah, to pull out the key ideas, what makes this AEL tick and what it could mean.
Absolutely. We're talking tiny nanoscale bots floating in the air, harvesting energy,
Huh.
all the way to quantum batteries, which sounds mind-bending in itself, and this global wireless energy network.
It's ambitious, to say the least.
So we'll get into how it's supposed to work, the big problems it wants to fix, and, let's be honest, the massive, massive challenges it faces. Ready to look up?
Let's do it. So fundamentally, you have to ask, why propose something so radical? The AEL really stems from the problems we're all familiar with in our current energy setup.
Yeah, like renewables. Solar, wind, they're crucial, obviously, but they're intermittent. Sun goes down, wind stops blowing.
Exactly. That unpredictability is a major headache for grid stability. You need power all the time.
And then there's the grid itself. The wires, they're surprisingly fragile, right? Storms, physical damage, even cyber attacks.
And they're lossy. You lose a decent chunk of energy just transmitting it over long distances. Plus, think about the land use.
Oh, yeah. Huge solar farms, wind farms, they take up enormous amounts of space. Land that could be used for other things or just left wild.
Precisely. And energy storage is still a bottleneck. Lithium-ion is dominant, but it has limits, Cost, how much energy it can hold per pound, how long it lasts after charge cycles.
It's good, but maybe not good enough for a fully renewable future on its own.
That's the argument. And layered on top of all that is the climate issue. We need carbon removal, maybe even some form of climate intervention, but these are usually treated as totally separate problems from energy.
So the AEL tries to weave it all together. Instead of separate fixes, it's this holistic vision.
Right. It essentially proposes turning the atmosphere itself from the ground up to the edge of space into an active piece of infrastructure.
Using what's already there, like sunlight, wind.
And more. Using the atmosphere's sheer size, the temperature differences, the natural electrical fields, even the movement of plasma way up high in the ionosphere, tapping into all of it.
Okay, so how does it actually do that? What are the components?
It's built on 4 main subsystems designed to work together across different atmospheric layers. First up, you've got the stratospheric and tropospheric harvesting nanoswarms, STHM for short.
Nanoswarms, that sounds intense. Tiny robots.
Tiny autonomous units. Think gram scale, maybe like a large speck of dust made from advanced stuff like graphene or carbon nanotubes. Billions of them, just floating in specific layers.
Billions. Wow. And they just collect energy.
They're multi-harvesters. That's the key. They grab energy from multiple sources simultaneously. Solar, obviously, using super efficient cells, maybe perovskites or quantum dots.
Okay, so da-da-da-da.
But also kinetic energy. They use tiny piezoelectric elements like fluttering membranes or microturbines to convert wind shear and turbulence directly into electricity.
So turning random air movements into power? Clever.
Yeah, and thermal energy, too. Exploiting temperature differences between altitudes or day and night using thermoelectric effects, even harvesting the faint natural electric field of the Earth.
It's like squeezing energy from every possible source up there.
Pretty much. And these aren't just passive collectors, they're smart. AI-driven swarm intelligence helps them organize themselves, move to the best spots for energy, dodge bad weather.
Like a flock of birds, but for energy harvesting.
Kind of, and they sense the atmosphere constantly. Oh, and one more thing, and they can have coatings, like metal organic frameworks, MOFs, that passively grab CO2 molecules out of the air.
So they clean the air while making power. That's quite a bonus.
It's all part of that integrated vision. Okay, second system, and this one is maybe the most revolutionary, the Quantum Coherent Atmospheric Batteries, or QCAVs.
Quantum batteries.
Right.
Right. This is where my brain starts to bend. How is this different from, say, a lithium-ion battery?
Totally different principle. Normal batteries store energy chemically. QCAs propose using special engineered materials, things like topological insulators or doped crystals, to store energy as quantum coherence.
Quantum coherence. Okay, layman's terms. What does that feel like?
Think of it like this. Harvested electricity excites quantum states in the material, creating a highly ordered, synchronized energy state, like a perfectly tuned wave that holds its shape. It's not random electron movement, it's a collective, coherent quantum state.
And that stores the energy.
Yes, and the magic is releasing it. A small trigger, like a specific signal or resonant coupling, can make this coherent state collapse, releasing the stored energy as a coherent electrical current. The theory suggests minimal energy loss during storage and release. They're targeting over 95% efficiency.
95% round trip. That's huge.
Game-changing, if achievable. And the potential energy density could be vastly higher than chemical batteries, too. It tackles intermittency head-on by storing massive amounts of energy very efficiently.
Okay, that's storage. What about continuous power? Baseline power?
For that, we go higher up. System 3, the Ionospheric Dynamo Tether Network, or IDTN. This aims for predictable, continuous power, totally independent of weather down below.
The ionosphere, so way up there where the plasma is.
Exactly. It taps into the kinetic energy of the ionospheric plasma itself, which is constantly flowing, driven by the solar wind and tides. It's always moving.
How do you grab energy from plasma flow?
With electrodynamic tethers. Think long, very lightweight, but strong conducting ribbons. Maybe aluminum tape strengthened with carbon nanotubes deployed from high-altitude platforms.
Okay.
As these tethers sweep through the Earth's magnetic field, which is always present up there, it's basic physics, Faraday's law. A voltage is induced along the tether, driving a current. You generate power directly from the motion.
Like a generator using the Earth's magnetic field and plasma wind.
Essentially, yes. Each tether could potentially generate significant power, maybe kilowatts to megawatts. It provides that steady, reliable baseload power to complement the more variable STHN harvesting.
Right, makes sense. So you've got harvesting swarms, quantum batteries, ionospheric tethers. How does all this energy get where it needs to go? No giant space cables, I assume.
Definitely not. That's a fourth system, resonant atmospheric redistribution, or RAR. This is the wireless grid component. It aims to completely replace vulnerable, lossy wired grids.
Wireless power transmission to the atmosphere. I've heard of that, but isn't it really inefficient?
That's been the challenge, yes. But RR proposes a more advanced approach. Energy from the QCAs is converted into highly focused, coherent beams, microwaves, or lasers.
Okay.
These beams are transmitted between STHN platforms or down to ground stations using phased array antennas or laser systems. The resonant part is key. They're tuned to specific receivers.
And the adaptive part, the atmosphere isn't exactly stable.
Right. That's where the STHN network's sensing capabilities come in. Using built-in LiDAR and radar, they constantly map the atmospheric conditions in real time.
Atmospheric tomography.
Yeah. This data allows the system to dynamically shape the beam and correct its path, compensating for turbulence or changes in density to minimize energy loss and ensure it hits the target precisely.
So it's like a smart, invisible atmospheric power grid.
Exactly. A dynamic, peer-to-peer energy lattice, power routed instantly from where it's generated to where it's needed anywhere on Earth, in theory.
Okay, and overseeing this whole dance.
That's the final piece, the Integrated Atmospheric Management System, or IAMS. Think of it as the AI brain.
Using all that sensor data from the STHN swarms.
Precisely. Synthesizing petabytes of real-time atmospheric data to optimize everything where the swarm should be, how to route power beams, predicting weather patterns, ionospheric conditions.
And you mentioned climate management earlier.
Yes, the IMS enables that too, integrated right in. Remember the CO2 capturing MOFs on the STHN? The IMS could coordinate them to descend to collection points when saturated.
Active carbon capture as a side benefit.
And potentially, more controversially, using the RAR energy beams for localized atmospheric modification.
Like weather control.
On a subtle level, perhaps. Gently influencing stability, maybe seeding clouds, dispersing fog, or potentially mitigating storm intensity. But the sources are very clear. This aspect needs extreme caution.
I should hope so. The governance implications alone are staggering.
Absolutely. Robust international oversight would be non-negotiable. So if you step back, you see how the whole AEL system is designed to address those core energy problems we started with.
Right. Intermittency. Tackled by harvesting diverse sources plus the QCAB storage.
Yep. Grid vulnerability and losses. Gone, replaced by distributed generation and resilient wireless RR.
Land use. Moved off the ground and into the atmosphere.
Storage limits. QCBs promise higher density, efficiency, and cycle life.
Baseload power. That's the IDTN tapping the ionosphere.
And environmental impact. Zero operational emissions, built-in carbon capture, potential for climate resilience. It's comprehensive.
Okay. It's an incredible vision. Almost elegant in how it connects everything. But how real is any of this? Is it just theoretical hand-waving?
That's the critical question, and the answer is complex. It's not entirely hand-waving. The AEL cleverly integrates concepts that are being researched, some quite actively.
Like the nanoscale harvesters.
Yeah, progress in lightweight solar cells, microenergy harvesting from vibrations or airflow, swarm robotics, these fields are moving fast, but
But scaling to billions of autonomous, durable units operating for years in the harsh atmosphere, that's a whole different level of challenge.
colossal. Absolute colossal engineering and manufacturing challenge. Then there's quantum storage.
The QCAs.
People are working on quantum batteries. Prototypes exist that show stimulated energy release from coherent states. But scaling that up to grid-level energy storage, maintaining that delicate quantum coherence at large scales, possibly near room temperature, that requires fundamental breakthroughs in material science and quantum control systems that we just don't have yet. It's still highly speculative.
Okay, what about the tethers? IDTN.
Electrodynamic tethers have flown in space. NASA, JXA, they've done experiments proving the principle works for power generation or drag.
Right, I remember some of those.
But operating them continuously in the denser, much more complex and dynamic environment of Earth's ionosphere is a tougher proposition. Material durability, stability, power management, new challenges.
And the wireless power, the RER system.
Again, research exists. Mid-range wireless power transfer using resonant methods is improving, but beaming power efficiently and safely over long distances through the turbulent atmosphere, that's a huge hurdle. Beam wander, atmospheric absorption, scattering, ensuring it's safe for aircraft, wildlife, people on the ground.
Yeah, safety seems paramount there. You need pinpoint accuracy and control, constantly adapting. Requires massive leaps in adaptive optics, beam forming.
Exactly. And the materials for everything. Graphene, nanotubes, composites, they promise amazing properties, but making them durable enough for decades of UV radiation, atomic oxygen, temperature swings, icing, that's another frontier. Manufacturing billions of these devices affordably maybe needs self-replication tech or something equally advanced.
So it sounds like every single component, while maybe rooted in some real science, requires monumental leaps forward.
Pretty much. Which brings us to the risks and hurdles, which are, frankly, enormous. The sheer scale and complexity are unprecedented, controlling billions of devices globally in real time.
Mind-boggling. And the quantum storage is still largely theoretical at scale.
Wireless power, safety, and efficiency over long atmospheric paths is a major, major unknown. Getting that wrong has serious consequences.
And interacting with the ionosphere on that scale, could it mess with radio communications, satellite operations, natural processes we don't fully understand?
Potential unintended consequences are a big concern. Then there's the climate intervention aspect. Even subtle weather modification carries profound ethical questions, governance nightmares, geopolitical risks. What if one country's attempt to disperse fog affects a neighbor's rainfall?
Yeah, you'd need incredibly robust international agreements before anyone even thinks about deploying something like that.
Absolutely essential. And the cost. We're talking astronomical figures, likely trillions. It would demand global cooperation on a scale we've never seen, plus radical cost reductions across multiple advanced technologies.
Not to mention just maintaining it all.
Yeah.
Billions of things floating around. What happens when they fail? End of life. Space debris is bad enough. Atmospheric nanobot debris.
Durability, maintenance deorbiting, recycling, huge life cycle challenges. And finally, governance. Controlling a global utility layer like this. Huge potential for misuse or weaponization, ensuring equitable access, security. It requires bulletproof international frameworks.
So the path forward is basically more research. A lot more research.
Across the board, yes. Advanced modeling of how all these atmospheric energy harvesting physics interact. Developing those robust quantum materials. Simulating the wireless power transfer with high fidelity, focusing on safety and efficiency.
Miniaturizing and hardening the nano devices. Creating the AI for coordinating these massive swarms and managing the whole system.
Prototyping tether segments, and maybe most importantly, starting the conversation now about the international governance needed for anything remotely like this.
Okay, so here's where it gets really interesting, despite all those hurdles. The AEL, it isn't just another energy idea. It's a truly radical shift in thinking, isn't it?
It absolutely is.
Moving from ground-based, often centralized power
Sure.
to this symbiosis with the atmosphere itself. using the sky as a utility layer, even if the full vision is decades or centuries away or parts prove impossible.
It acts as a kind of North Star, doesn't it? Pushing the boundaries in multiple fields, nanotech, quantum physics, AI, material science, atmospheric science, and forcing them to connect in new ways.
Yeah. If we connect this to the bigger picture for everyone listening,
Yeah.
the AEL really underscores that solving our biggest challenges like energy and climate might require thinking way beyond just making current tech a bit better.
Exactly. It forces that question. Not just what's feasible next year, but what could become possible if we really push the frontiers across disciplines. It's about system-level transformation.
So the final thought for you to chew on, given those immense challenges we outlined, but also the incredible potential, what level of global cooperation, what kind of ethical foresight would we actually need to even start seriously exploring something this profound, this deep integration of technology with planetary systems?
It really makes you wonder, doesn't it? Is humanity actually ready, institutionally, ethically, collaboratively, to take on that kind of active management role for Earth's atmosphere? That's a huge question.